is a relatively shorter presentation today because I couldn't find time to prepare anything detailed. But it is in relation to what we have been discussing on churn modeling. So we saw a couple of other use cases of churn modeling in the B2B software as a service scenario. So this is churn modeling, but in a different sector, that is in electronic banking. Okay. And this is relatively simpler than the ones that we have seen in the past, both in terms of the data involved as well as the modeling techniques implemented. But what I would like us to draw our attention to here is two particular techniques that they have used. So though the modeling and all those things straightforward, they have used a couple of interesting techniques here, which will make a very complicated modeling scenario a bit easy. Okay. So this was the process that they followed in the project. So this was for a bank offering internet banking services. So the people who built the predictive model, so they understood what the bank was doing, who the customers were, and what are their distributions, what is their age range, what are their income levels, what are their education levels, and so on. Okay, so that comes under the first two steps, that is the business understanding, data understanding, and then the data pre-processing, and then the modeling. Now, so those 2 points that I mentioned, which I consider to be important, so they come under those two steps. That is the data pre-processing and the modeling phases, and then comes the evaluation and the deployment. So these were the details on the data and some minor details in the project. So they had 4,383 customers, and the duration of the data spanned from for 2 years. That is from March 2013 to March 2015. And wherever they found missing values in the data, they did a mean imputation. So they would take an average. So the percentage of missing values was not that high. It was in around 1 or 2%. So they were able to go ahead with this imputation. Now what we should remember is imputation is a good technique for filling up missing values. But if you have a large number of missing values or a large proportion of the variable that is missing from the data, then it is not a good idea to do imputation. It is better in that case to drop the variable altogether from the model. But here, since the amount of missing variables was not that high, they did a mean imputation. That is, just take an average of the existing values in that column, and wherever there is a blank, just put in that average value. So this was what they did. Another technique that is generally followed for imputation is the regression-based imputation. Now, this is a slightly advanced technique which people follow when they are dealing with more complicated data sets. Now, the next step that they did was something called as Bootstrap Sampling. Okay, so the reason for doing the Bootstrap Sampling is to resolve the class imbalance. So they had 4,383 customers, and they were trying to model churn. Okay, but if you look at the data, the amount of churned customers is just 63 out of the 4,383. That is only 1.4% of the customers had churned. Okay, now whenever you're dealing with this kind of a churn problem, this class imbalance scenario is something that you have to handle. Okay, and in the past weeks as well, when we were discussing the predictive models on the B2B software as a service, they also had this problem. Okay, and if you remember, they used a different technique called as SMOTE. That is the synthetic manual oversampling technique. So that technique is more of a it's a bit different technique, which we call it as an oversampling technique. Typically, you follow an oversampling or undersampling. Okay. Now, bootstrap sampling, what I have mentioned here in the fourth point, is another technique for you to reduce the class imbalance of the data. So, what this bootstrap sampling method does is, it takes multiple samples out of the data with replacement. So when I say with replacement, what it means is a number or an observation which is present in one particular sample can also be present in other samples. So that is what we call as with replacement. So you specify a number of samples that you have to take. So you have like 4,383 observations, right? And you have, out of these 4,383, 63 are the churned customers. So you take a specified number of customers from the remaining customers, apart from the 63 customers, the non-churned customers, you take a specific number of customers as a sample, okay? You specify a number for that sample, and then you take multiple samples, okay? For each of the samples that you take from the non-churned customers, what you do is you combine the churned customers and then you make the predictions, okay? So like this, you take multiple samples and then you see which sample yields the best possible result. So that is what is called as bootstrap sampling. So this was one of the techniques that I mentioned, which we should take away from the session, okay? The other technique that they used was the backward elimination for feature selection. Now, backward elimination, how it works is typically, how do you iterate your machine learning models? It is based on the feature engineering, right? So there are two ways to do it. So one is called as forward selection, and the other is called as backward elimination. Forward selection is it is something similar to a bottom-up approach. So you start with one variable which you feel is important, you feed that into the model, and then you see the results, okay? And then you feed in certain other variables additionally on top of the original variable that you fed in, okay? So and if there are any additional features that you would like to create, you create them using the existing variables, and then you feed them as additional features to the model. So this is the normal feature engineering process that you follow. This is what we call as forward selection. Now, backward elimination is something like a top-down approach. In the first iteration of the model, what you do is you build the model with all possible features. So the existing features that are already present in the model, and on top of them, if you feel you can create certain additional features, then you create those additional features, and then you build the model. So the first iteration will contain all possible features, okay? Once you create that initial version of the model, what you do is you take the p-value of each of the features that you have used in the model. Now, when you do a linear regression in Microsoft Excel, for example, at the end of the regression, you have a list of the features, and then the p-values are also listed against each of those features, right? So you take the p-value for each of those features, and then you eliminate those features which are having a p-value of greater than 0.05. So usually the alpha or the significance level that we use is 5%, right, or the 0.05. So if the p-value of a particular feature is greater than 0.05, then you eliminate that feature from the model. And in the next iteration, you will only use those features which are having a p-value of less than 0.05. That is what we call as backward elimination. In each subsequent iteration, you will put in those features, you will see the p-value for each of those features. You will eliminate those features which are having a p-value of greater than 0.05. Okay. So that is what we call as backward elimination. And then the technique that they used here was a relatively simple technique. So they built a decision tree model, okay? And they also did a cross-validation for evaluating the effectiveness of the model. So they split the data into 70% of the data was trained, and 30% of the data was testing data. And certain variables that they used were, so these were the variables that they had listed in the paper. The gender, and then complaint. So this was a binary variable. That is to say, if the customer had raised a complaint or any grievance to the bank in the past, then it would take a value of 1, otherwise it would take a value of 0. And then they had education level. So whether the person has a degree or whether he just knows to read and write, and so on. Okay. And the length of the customer association. So how long has it been since the customer joined the bank? So these were the variables that they used. And then they built a decision tree model. So the advantage of decision tree is when you compare it with a black box model such as a random forest model or a boosting model, decision tree you can actually visualize. Okay? And this is what they had done. And so this is how a decision tree algorithm typically works, right? So here they used a metric called as the Gini index. to determine the variable split. So what will happen is, in each step of the decision tree, it will calculate that the algorithm will calculate the Gini index metric for each of the variables, and then it will determine that particular variable for which the Gini index is the maximum. Okay, so that is what they have done over here. So in the first step, if you see, they had certain other variables as well, but then when they calculated the Gini index of each variable, they found that the Gini index for this variable is the highest. That is the number of transactions through USSD based mobile banking. Okay, and then in each subsequent iteration, they identified the right variables based on the Gini index, and then you can see the other variables as well. So if age is greater than 53, less than or equal to 53, or if it is greater than 29.5, less than or equal to 29.5, and so on. So, and the last node of the decision tree is basically whether or not the person has churned coming via that particular journey. Okay, so this was the model that they built, and the results of the model were as follows. So in these kinds of models, you generally don't consider the accuracy of the model, but rather you consider the precision. So accuracy here was around 85%, but more than the accuracy, it is the precision which is important. The precision formula is like true positives divided by the true positives plus the false positives. That is, of the total number of people who had churned, how many of them were your model able to predict? So we know that 63 customers had churned, right? So out of the 63, how many of them were accurately predicted by this particular decision tree model? That was how they defined their evaluation metric. And so before the feature selection, so when they put in all of the features in the model in the very first iteration, they got a precision of 72%. But then when they followed this backward elimination technique, eliminating the features based on the p-value, when they arrived at the final set of features for which all of the p-values were less than 0.05, they had a precision of 95%. So yeah, that's what I had for today. Relatively short presentation, but since I was involved with other things, I couldn't find, I was not able to prepare anything more substantial. Any questions?
Sai, in the churn example that you talked about, like let's say 100 customers is what we have, and it predicted 50 going to churn, but the 50 that's the model predicted are retained in, but other 50 members churned out, then what would be the number that we're going to see? It's 0% or whether it's 100%? But because the number is same, the model predicted 50, churned out customers are 50, but they are a totally different set of customers.
So you're saying, so the customers who had not churned actually, but the model predicted that they have churned, you know?
Exactly, right. So let's take two groups, group A, group B. Churn model predicted that complete group A going to be churned out, right. But group B actually basically churned, and group A completely retained. Let's take group A is 50 members and group B is 50 members.
Yeah, so that is where this precision metric comes in. So the base or the denominator of the precision metric is the actual total number of churned customers. So let's say the 100 customers churned, right? So that will be the denominator. Out of those 100, how many were was your model correctly able to predict? So that is what we call as precision. So the remaining, the model might have predicted that they have churned, but in fact they have actually not churned. So that is, I think that is what we call as the true negative, or I don't remember the exact technology here, but that will come under a different category, which is not considered under precision. And that is also the reason we use precision as an evaluation metric, because that is what we are concerned about here.
So we'll be going by customer, saying, okay, let's say 50 customers are churning out, so we'll be knowing who are those 50 by this model, right?
Yes.
Okay.
And when so that is how you evaluate the model because if your model has is having a high precision, right? So out of the 50 customers who have actually churned, if your model is able to predict around, let's say, 40 to 45 of them, then you can say that the model has learned well from the patterns, and you can confidently apply the model to a future incoming customer to actually predict whether or not that customer is going to churn. That is why we don't go for accuracy. So accuracy will mean the true positives as well as the true negatives. So both those things we will consider. But in precision, we are only concerned about accurately predicting the churned customers. So the actual metric that you use for evaluation, whether it is precision or recall, that depends on the business situation. Okay, so you evaluate the cost of, whether it is more expensive so where is it more expensive to make a mistake? Okay, can you afford to not predict a customer who is going to churn, or can you afford to predict who is not going to churn? So that is a trade-off that you decide based on the business situation. In this kind of a churn situation, it is more important to predict who is going to churn out of the churned customers. That is why we use the precision as an.
So typically in medical cases where you predict whether a person has a disease or not, then false negatives should be minimized, because when a person has a disease and you predict they do not have a disease, then it's not good. But if a person doesn't have a disease and you predict they have, they can always come in and then have it checked and then get the reports and go off. It's not that big a deal. Okay, so at the cost of causing that inconvenience, you are predicting all the people who have the disease actually. So that is, false negatives are important when it comes to medical cases. And when it comes to alarm situations and all, the other one is important. Like, you shouldn't cause disturbance to people, using a false alarm.
Yeah.
And they'll get fed up and then change the whole system.
There they will actually calculate that false positive percentage. That has to be very, very less.